Hello? It's Madhuri? Yeah.
Hi, how are you doing?
All right. How are you?
I'm good.
Good. Just waiting for people to show up here, and I'm putting a message in right now so people can. Sometimes we have some technical difficulties early on, and
Right, yeah.
so how have you been this week?
Yeah, it's been good. I got some time to look at some of the projects on the repository, and hopefully I'll be able to discuss it in detail with you tomorrow.
Okay, yeah, that sounds good.
Yeah.
That sounds good. Hello, Jesse. Is it Jesse? Yeah. Oh, I think he dropped off for a minute. There he is. There, Jesse? Oh,
Sorry. My mic isn't quite working right now, so.
okay. I thought that was Avery earlier. I didn't know if it was.
No, in between things here.
Okay.
I'll be like fully there in a moment.
All right. Well, thanks for coming to the meeting. I don't know who else will show up, but maybe we'll get started now. So this has been an eventful week on the Slack. We had just a lot of traffic on there, and that's good. That means that our Slack review will have to be sort of the best hits, so we can review it and see, maybe some of the things and follow up on some of those. Better,
Yeah. I don't really know how you want to structure that today because I posted just before the meeting in Slack kind of some of those best hits basically.
Okay.
And I don't know like what are major presentations for today outside of news updates. Like I know you have the Rockwire event you want to talk about, Daniel's paper, and I have a whole bunch of things to talk about. So I don't know how you want to.
Well, let me go to the general, the one you posted in general, and I'll get it up and we'll go through from there. So let me start with this. So we have, you see my screen here?
I see darkness.
Oh. Let me reshare it.
This be me.
All right. There we go. So yeah, all right. So
Okay.
So we have Slack. Daniela's new paper. Yeah, Daniela wrote a paper on is like economic metabrains. So she's taken the metabrains concept and she's combined it with active inference and the free energy principle. And she's gotten something really nice out of it. I was reading it over and I sent her some comments, and so it's on one of the channels. We might go over that. Madhuri and myself and Jesse are also meeting tomorrow on some, sort of more in detail research things. Madhuri, did you want to give an update now, or did you have anything to?
No, I think I'll discuss that tomorrow, if that's all right.
Yeah, that's good. Yeah.
Go
ahead.
Perhaps later I could probably very briefly outline what I would be discussing, and if you have any thoughts, you could share that.
Yeah. Okay, let's see. Ankit Grover has a Medium post libraries and an experiment with Copilot. So this is a thing that Ankit sent in the Slack, and he was talking about this last week. This is the genetic algorithm with reversals. This is like Colab notebook that he's produced, where he's plotted out a lot of these things with his algorithm. He's prepared a genetic algorithm. He's done this thing where he's reversing some of the steps, and I can't remember exactly how. I didn't pull up the medium here. I just pulled up the Colab and was looking at it. So it goes from a minimization process to this other process, and it reverses itself over time. And this is supposed to improve performance. I have a talk today. I'm going to talk about switching, and as it turns out, this is something you see in nature a lot in different systems. So I'm going to talk about that later. He prepares this, this domain, and he implements the algorithm on this domain, and he's able to get a better performance than he would otherwise do. I don't think he did a formal experiment here where he compared this to a non-reverse GA, but I wish he were here. He could explain this to us, what exactly he did here. So maybe if he shows up later, we'll come back to this. I have an upcoming event with Rockwire. I'll talk about that. Jesse has and his NSF fellowship updates. We have some things in Cognitive Features, and this is also Jesse. This is multimodal machine learning, spatial computing, and NeurIPS metacognition, which is that workshop that we talked about in the submissions document last week. Abiba Burhani news. This is a person from AI Ethics, who I think Jesse he'll update us on that. Update about alumni for Valeria, who is someone that Jesse's worked with, her thesis, Angela's projects, Avery and EA grant-related news collaboration. So we'll talk about that later. And then Jesse will also talk about position papers, and this is like a type of paper where you write an argument for or against something. So he's going to talk about that. Maybe how to write them, but we'll see. And other updates from Developmental AI Open Chat Forum, NeuroMatch. So that's a nice recap. So why don't we go through some of these? Like I said, there were so many things in here this week, I can't begin to go through one by one. So why don't we go through some of the more active channels here? Let's go to Cognition Features. So
I tried to link the active channels, and that was basically the point of that post, because those are most of the ones that I've seen, but not all of them, obviously. So
right. So we'll do Cognition Features first. So this is Johan John's. I don't know if this is his site or what this is, but this is So this is his blog, and he has a bunch of posts on representation. So we've gone through some of these posts, but this is the source for this. He's put out a bunch of posts on representation, and this is something that we just wrote the Metabrains paper. We talked about representation quite a bit, but it's in general it's a very muddled and hard area to get your head around, because it's there's so many different definitions, and what does it mean to represent something? I could represent something as a sculpture. I could represent a horse as a sculpture, but that's not a real horse. And so when I say I'm representing it, I'm just taking features from the horse and I'm putting it into the sculpture. But there are no rules as to what features necessarily belong there. So there are these debates about what do you put into a representation? And then of course in the brain, this is not something you build intentionally necessarily. This is something that exists as a way to represent objects in the environment. So neurons might represent faces or locations in space, and this is quite different than the artistic version. So this is why it's kind of messy, because there's a popular version of the word, then there's this technical version of the word, then there's philosophy and neuroscience and even modeling. So there are a lot of different sort of competing ideas going on there. So
I would also mention, just for those who are newer to the lab, it's not active anymore, but Johan John has been running a kind of a discussion group for it sort of picks up in the summer and dips off when everybody's busy in the fall and stuff again. So it's kind of in a hibernation mode, sort of, because he's a professor here. I used to here in Boston. I've yet to meet him in person, but I've had a lot of online engagements. But they've covered a lot of things from like emergence to causality to representations and all kind of manner of things like that. And it's a really, really wonderful thing. So when it starts up again, people are interested, let me know. We can, onboard some people there. But I strongly recommend these readings. I have yet to finish all of them because I just feel like Johan's sort of like what I would really want to be if I was like a physicist who went into neuroscience and went that way. He's sort of the opposite. I feel like him and I both have a very strong desire to look at the same kind of things, but his path is like the Gaia sense, and he's very particular about that. And it's really great to see if follow him on Twitter. I strongly recommend that, or like if you can Facebook friend him or whatever, because the discussions he gets into are really relevant, and a lot of things we do is like really computational, and in this lab, and this there's like DevoWorm and everything else that we do, and that's great. But there's like it's just a really good counterbalance to heavy computational stuff, and the way that he talks about the discussions he gets into people when he tries to explain or discuss representations is really, there's a lot of insight to be had there. So I could say more about that later if you're curious, but like just wanted to really mention that because it's very, there's a lot of good stuff in these discussions.
Hey, so can I quickly interrupt?
Yeah.
And since you mentioned about Johan, was he also running a Stephen Grossberg's book club or something? Like, where you
Yeah.
I've been, right. I've been meaning to be a part of that discussion sometime.
Yeah. That is the discussion group I was just mentioning. I believe he has a YouTube channel, and a lot of the past discussions are on his YouTube channel from that book and from other things. And absolutely, like, if I would totally endorse, like, if you want to go through that, and, like, even the videos or some of his writings and just talk about them in the lab at any time, like, I'd totally be into that, because they're very rich. Johan's sort of one of my favorite academic people.
Right.
So, yeah.
Yeah, that's great. We talked about Grossbergian neuroscience several weeks ago in the lab groups. This is before Madhuri joined, but so that we have that in some of the videos. So this is a paper on GSLAM, which SLAM is simultaneous localization and mapping, and it's something we haven't talked about too much in this group, although it's a very big deal in like virtual environments, virtual reality, and I guess in AI as well. So this idea of simultaneous localization and mapping. It's a fundamental problem for autonomous embodied systems, and he talks about this in a sort of a free energy principle, active inference kind of framework. So there's that. That's a preprint from Adam Safran.
I hear it was inspired by the Spice Girls and one of their hits about, anyway, that's a dated reference at this point, but yeah.
Yeah.
Anyway, thank you for that.
Yeah.
Oh, I'm going to try to log back in and use my mic part. Yeah.
All right. So as Jesse comes back in, we're going to talk about the Ethics Society and Tech channel. Jesse posted something on AI safety. It's a reading from I guess it's from the Bear Lab at Berkeley, the Bear blog. Then there's Abiba Burhani, who actually, Jesse says she's going to let him proof her thesis. So she's doing a PhD thesis, and Jesse might be able to get a chance to read it over in its early stage, or it's whatever stage she's in, and give feedback. So do you want to talk about that a little bit, Jesse? Or
Yeah, I don't really understand what's going on with my when I use just my Mac computer, it's not doing very well. Anyway, if you could maybe just open the tweet. Just click on the link.
Yeah, I don't know if I can do that though.
Oh,
you want to share your screen or?
Well, let's see. Let's see if I can.
Okay.
It's not that important actually. Basically, what I'll say about this is am I even here still? Okay. What I'll say about that is for those who don't know, Beba Birhane is someone who is really trying to do some innovative work that if you particularly care I retweeted something because it started out with she posted this gif of a cat trying to squeeze into a very small box, and it was not really working out for the cat, but was trying to get in there anyway. And she was saying, "This is me trying to defend trying to put my non-traditional CS computer science thesis into a traditional CS box when she's defending it, basically, or preparing it for dissertation and stuff like that." And I retweeted it saying, "Hey, this will be me in a few years, hopefully." and in the comments to her own original post, she's like, "Oh, anyway, by the way, if you would like to volunteer to be reviewers or proofreaders of my thesis, let me know." And I reached out because we follow each other, and we sort of know each other, like through internet, which is what it is. But anyway, she basically said, "Yes, you can review my thesis," and that's really cool because Birhane is. I admire a lot of the work she's trying to do to bring outside, progressive, and basically critical perspectives on AI ethics, and she has some innovative things about relational ethics, and it's just kind of an interesting organic development of that. So she's someone we mentioned a few times in the past, and it'd be cool to have a more direct interface with her. And that's actually I may also I mentioned her earlier. She's not. I mentioned Valeria, who's also an AI ethics, kind of one of the original people on the team a few years ago. I may also try to loop Valeria in on that because it might be related to what she's doing herself. Valeria is a law student, actually in Chile. But unrelated, and I'll just mention here because the most closest thing to it is Valeria is also preparing her own thesis, although it's sort of it's sort of like undergrad and masters because of how they do it in her country of Chile. So she's also writing her thesis now, and there may be some overlap between that and other things in the ethics team. So that's cool. More about that later, but I wanted to just mention that there's still some ties there, and good things are happening there, and we wish her the best in that sense. So
yeah, that's great. All right, so then so we have that. I think that's it for that channel. Okay, Ankit's going to join us in a few minutes, so that's good. Let's see, professional development is the next channel, and this is where we had, I think probably back to this point. Deepmind internships are open across various countries, so this is Deepmind, which is offering these internships if you want to check it out. This is for people who this is in research, engineering, science, ethics, and society and operations. So I don't know what level these are. I imagine all different levels of expertise. But these are remote opportunities, so you don't have to be in any one place. Although they have on-site ones as well. So, and this is, of course, Deepmind is a machine learning, deep learning type organization. They do a lot of really innovative work. So check that out if you want to, if you have the opportunity to do that, interest. Jesse says, last week I gave a very small talk on some materials for the NSF Fellowship Program. Let me know if you want to see them. So this is a response to that, and yes, Madhuri wanted you to supply those, Jesse. So I recommend for some of this professional development stuff that we create a repository for it. So like this could be on Google Drive. If we wanted to I have a repository of things for people, and I don't use it much anymore. But I have a very large collection of various readings on different topics in professional development, and I should provide that to the group here again, because like I said, I haven't touched that repository in a couple of years, but it has a lot of different topics. Not all of them are relevant to everyone, but it would be nice if we could put together, a master repository of those materials. So that's a good way to just, if you get something, Jesse, like a document or something you want to review, oh, hi Morgan, how are you? Let me know. We can put it into a centralized repository for that, so people can read it and respond.
Yeah, I think that's one thing that I'm going to. That's something we have to figure out regarding Notion versus GitHub, because Notion's very good at housing some things, but it's a little bit harder to interact with. So we can talk more about that later. But yeah, I was going to say Morgan is here too, so that's cool.
Hello. Okay, so then we have, let's see, any particular topics people would like to have covered with respect to professional development. So now we're going to have, I think Jesse's going to host a segment on this for, continuing on in our meetings. So what kinds of topics? So Ankit suggested tailoring your resume for research roles and industry research roles, cold emailing, doing research independently and finding a mentor if you're doing so. And then, yeah, I said that their best practices, it's just a matter of putting these materials together. So, there are a lot of things I could tell you kind of from personal experience, but it's best to have some best practices to think about and put down on paper. So I haven't done anything on that this week, but that's something we can do in the future. And then Jesse's going to give a talk on position papers in a bit. So that's professional development.
Yeah, that talk would be very minimal, and I might sort of defer to you in that. I have a web page I might just briefly show, a very, very, very quick talk, so nothing major.
All right. This is another tweet here from Jesse Gregory Cohn, who's a developmental person, philosopher, that sort of thing. So he says, one thing I noticed in passing is the discussion of information for developmental endpoints. The framing is still linear, albeit complicated from genes to behavior, rather than a reoccurring web of reciprocal interactions involving but not privileging genes. So this goes back to Patrick Bateson. Let's see, where do I start here? I persisted in the use of the word innate. I tried to adapt, at least in part in this book, using circumlocutions such as not learned. Circumlocutions means how to describe something more specifically, I guess. Such as not learned or independent of specific experiences. Nonetheless, as I always replied to Pat, and as you may understood by reading these pages, this is still an important meaning for me in the use of the term innate, which depends on the type of question a scientist is interested in. So this is this idea we talk about innate versus learned in developmental psychology, even developmental biology. That some things are in the genome, or they're innate in some way, that they're passed on from to offspring from the parent, or that they're sort of in. Sometimes people just mean like it's biological, not necessarily learned from the environment. So there are different uses of the word innate, and it's kind of hard to, in AI, we've often talked about innate as sort of like standing in contrast to sort of the spontaneous learning that you would find in a deep learning system or in a machine learning system, where you're learning in associations from the network that you're running, and you can put labeled data in, but there's oftentimes not a lot that's innate. And so some people have suggested, well, if we add an innate component, some structure to the learning, that you can learn on something that has some structure, then that will improve performance. So there are a lot of definitions of this term innate, but I would definitely keep that in mind when we talk about that. That there a number of definitions that you can use. So in this, they continue. Of course, I know that the path that leads from genes to behavior is long and perilous, an inextricable tangle of genetic and environmental influences, as well as epigenetics, is what shapes behavior and its development. Patrick Bateson, like others, is dedicated his scientific life to disentangling them. However, the question relating to the origin of information is different from that of how this information shapes behavior. So again, we have this, sort of what's genetic, or the term genetic is interesting because it doesn't necessarily relate to genes per se. It relates to this process of transmission through like a parent. If you go back far enough in the literature, there's that's kind of how the term originates. And then this stands in contrast to environmental influences and epigenetics, which is another fraught word where you're going from this genetic to environment interaction, or that there's something that environment is triggering in the genome that produces this epigenetics, which is, sort of outside of genetics. So all these terms are, when you read these terms, sometimes you want to think about the etymology of the word and how people have used it, because sometimes that's key to understanding what maybe a new vision of what that is. Like if you think about epigenetics and you could read a lot about it and come up there. It's one of those things like representation, where it has like 6 or 7 different definitions.
Yes. I was just waiting for you to finish your point. It's like, it's a lot like representation, because depending on who you talk to, where they come from, if they're a biologist or computational or AI or like psychologists, they have all these different ideas about what it means. And it's sort of like the best you can do in some ways is just to like understand there's numerous dialects and sort of even historical influences within those fields or subfields or dialectical appropriate, wherever the vernacular is for that field of study, like what has shaped that has its own. This is why we're so big on trajectories. Like you gotta know that, and a lot of it. I'll even go directly back to things that Johan said about representations, that like you can get to a place where people will agree and disagree about the same word and the same usage, just depending on how it's approached, and it's just tough, and there's not really. It's so muddled because a lot of people want to approach representations, or especially in this case, innateness is like, that's been a major. I don't even know how to describe it. Peak to climb, with many different ways of sending it. And they're not even mutually exclusive, which is the tough thing. Like the perspective of a hardcore biologist coming to innateness and looking at genes and epigenetics in a particular way, isn't necessarily mutually exclusive to how a hardcore machine learning person who doesn't care about biology is looking at it. It's just the context is, so
yeah.
You move on, but it's tough. It's tough. The best you can do is try to be informed.
Yeah.
But,
hello, Ankit. How are you? We were just talking earlier about your demo the Colab notebook you put in the Slack, and maybe you can talk about this a bit later.
Yeah, sure, I could talk about it.
Okay. Welcome to the meeting. Welcome, Morgan, once again. And so, the other thing maybe I wanted to bring up about this, and I'm going to use my board for this, is sort of this idea of how like this relationship is set up. So like, we talk about innateness, right? And it's, look at this. Yeah, so we talk about innateness, and you can think about it as like this layer at the bottom. Like our Metabrains model, we have like our different layers of representations. We have like, let's say we'll do this type of diagram here, right? And I'll label the parts here. So A is the direct perceptual input, right? And this is where you're bringing in information into this system. And this system here with the two layers, or B and B prime, let's say. This is the representational layers, right? So this is a representation, what we call a representation-free layer. And so the idea would be that you have this system of, where you have direct perception coming into A, there's structure in the environment, and it's informing sort of the stream of information. The A is not doing anything to this information, but sort of funneling it into the metabrain. So, you have like different pieces of structure out in the environment, and they're all coming into A. And A has like maybe like a beacon at the end here. It's like maybe a camera or a visual beacon or something where it's pulling in information at a certain angle. And everything in that angle will come in and then just be a data stream into this metabrain. Now, this is where we get this situation where we have two layers of representation. So we go back to representation and we say, this bottom layer, which is representation free, this is a model like maybe like a simple neural net where there's no inherent representation in there. It's just kind of like a network that's connected together. The stuff we do with Bradenburg vehicles is kind of like that, where we have just a network from sensor to effector, and you get information going through. And maybe depending on the structure of the network, you get certain internal affordances where like information goes through an interneuron, or it just goes to a wheel from a sensor and it has a certain behavior. So there's no representation here. But in this layer, this is the representation-rich layer. And so this is a different behavior. This is where you might have like a semantic representation or some sort of dictionary that maps maybe things that happen in B, like different configurations of network activation into some meaning. So like, you might have like if these three neurons if these three interneurons in this model B are activated together, that might mean like that there's the agent is hungry. And so then we can reference basically between B and B prime. We have these connectors between them that give us information about like, we can map between like this sensory information, this thing going on in this representation free layer, and then this stuff in the representation. Now, this is all a metabrain with a sensory input. This is all basically, this is the environment here, right? This is the thing that's learning from the environment. So it's like being shaped by the environment. But it's also kind of has an innate component. And so this is the innate component here, which is C. That's the innateness. And this could be like an artificial genome. It could be like a set of instructions. It doesn't really matter what it is. It's something that this agent will inherit. So it's like it starts off, if we take like a neural net, it's initialized. So we start off at a certain initial condition, whereas sometimes physical systems will have an initial condition. Now that's not innate. We don't think of that as innate, but that's basically what it is. It's the initial condition. So this is this is like I'm trying to write on this pad. It's not, doesn't afford me the best penmanship. But anyways, this is an initial condition. This is an initialization of the model, but it's also an innate model because we can tie it to biology by having like artificial genes. We can have a gene regulatory network where we express the genes in certain amounts and then map each of these genetic components to some feature of this model. So we have this interaction between this and the agent and the environment. And so you can see how, this kind of resembles the brain where you're mediating the environment and genes with this sort of model here. And I've done the Metabrain model because it's a good example maybe of epigenetics, where you have like some genetic representation that this is a representation, but maybe a better word for it is encoding. In evolutionary computation, they use the term encoding. They use it a lot in computer science. But it's basically taking like these genetic elements, these initial conditions, and giving them some meaning. Like this thing here, this box, represents maybe some part of this topology in the representation free model. This box or gene or component maps to some of the representations in this B prime layer. And they all kind of have like a piece that they contribute. And then when these pieces are in place, then they can adapt based on what the environment's doing. So you can relax the weights between neurons. You can, maybe change the representation slightly based on what's, you can prune the dictionary of terms. You can do all sorts of things. But this is all dependent on environment, but it's all set up by this initial condition. I bring up the Metabrains model because I was having this really not a discussion, but I was reviewing Daniela's paper, and one of the things she doesn't really have, that she doesn't really define very strongly in it, is the Metabrains model. And I just wanted to go over that just to get it clear in my head, but also because it fits into our discussion. So Ankit says, I agree, Jesse, same ideas but different words, phrases, and definitions. So yeah, Ankit was thinking about some of the things you were talking about, Jesse. So I just wanted to go over that, and I know it's kind of an aside from our Slack review, but that was...
I think it dovetails really well into like some of the multimodal machine learning stuff. And I won't really go into that much today, but I think multimodal machine learning and some spatial computing stuff is going to add a very interesting layer to a lot of the integrative, like integrating the different multimodal, like integrating different sensor inputs, and in the top level of the layer is sort of where there's this mesh between the representations and the inputs, and I feel like that's a very interesting space to be looking at.
For multimodal neurons, actually, like a while back, OpenAI had done some small work on it. So I'm posting the link of it in the chat. Maybe if you want to take a look at it right now.
Okay. Yeah, this is OpenAI blog, multimodal neurons, and this actually is... Oh, I think I've seen this, yeah. So this is, this is nice because this is a representational sort of approach. And so this, let me share my screen here. So this is the link, and this is something, this is called CLIP. This is something that OpenAI has developed. What they have are neurons that respond to different concepts, whether they're presented literally, symbolic, or conceptually. So if they're presented, you would have a label on something. You would present it to the agent. It would be labeled so that there would be some activation of a neuron based on its sort of category, its context, and then it can, if you train it that way, you can classify things, and it's a better method for learning. This is the Quiroga et al. I don't know if it's the same paper, but I remember reading this at one time, so I don't remember if I have the. But yeah, so they've done a lot of work in the neuroscience literature on multimodal neurons. So you have like these neurons that respond to abstract concepts. So this is where you go into the brain and you say, what is the brain doing in terms of representation? Is it representing, like, we think of representation like that sculpture that I talked about. You take a picture of a horse or a sculpture of a horse. It has certain features of a horse, but it's not a horse in total. It's like, maybe like a two-dimensional representation or a representation of the face and the body, and you can tell that it's a horse, but it's not really a horse. Your brain is actually representing parts of something in the environment, and it could be like the shape, it could be the face. Neurons represent a lot of different things in the world. They can represent faces, they can represent abstract shapes, they can represent feelings, based on what the rest of the brain is doing. there are a lot of different ways. So there is this idea of the Halle Berry neuron, which is maybe also the grandmother neuron, if you've ever heard of that term. And basically what that means is that there are cells that represent sort of themes, or in this case maybe faces of famous people, or it's just some property of the thing in the environment that you're looking at. So if you see, or in this case it's the text Halle Berry, so just seeing that name, you can connect it with a face, you can connect it with a context. And so this is a really interesting paper because it kind of goes through some of the neuroscience literature on this, maybe some of the things that they've been able to do in machine learning, where you can take like a neural net and you can like specify different neurons for doing having different properties, encoding different properties. And so then this helps learning, it helps identification. So they implemented this in ResNet 50, and I think this is some of the things where I don't know if this is like style, kind of like a style transfer thing or what, where they have different categories, and here are the images that they've classified these things as. So like summer, winter, shocked. Did you have anything to add?
I like how Christmas has the Grinch face.
Yeah.
I appreciate that.
Did you have anything to add, Ankit?
No, I just want to share this. This is related to what you're talking about.
Yeah, thank you for that. That's a very good example. So yeah, that's good. Yeah, that's something we can follow up on, and I know that there's a lot to talk about there, but that's yeah. Let's put a pin in that for later. I know it was a kind of an indirect conversation because it goes from like the almost like this innateness up to like classification, but that's that's sometimes that's actually why people are interested in innateness, because a lot of systems, it's like it's a chicken and egg thing. Where do you start with like a representation? Where do you start with like identifying things? Do you have to stuff a bunch of training data into the model to get it to actually work, or can you just build something that's very generalizable? And yeah. So
also, is someone new here? Is that Avery? Or is that someone else?
It's me, Krishna.
Oh, Krishna!
Hi,
Hey.
Hi, everyone.
how are you?
I'm good. Thanks for writing me the letter of recommendation.
Oh, that's fine. Yeah. Oh, yeah. You're welcome. Yeah. I almost forgot
Thanks.
about that. Okay. Yeah. And so, yeah, for people who don't know, and I think three of you have met him. This is Krishna Katyal, and he's active in this group and in the DeVorn group. So he's interested in machine learning and things like that, deep learning, but also the brain. So welcome back.
Thank you.
Okay. So yeah, this is we're back at our thing here. So we talked about Dev AI, Open Chat Forum, had a lot of things. Now Jesse did a career fair at the University of Albany, which is his alma mater, this week.
Yeah.
And, did you want to tell us a little bit about that, or?
Whoops. Sure. I'll just. Whoops. I'm all over the place here. I'm not sharing my screen yet, am I? Okay.
No, you're not. Well, you want to share your screen? Okay.
I'll just really quickly share it. All right. The short version of it is yes. This covers it pretty well. Basically, curses the Center for Undergraduate Research and Creative Engagement, something like that. And I've been talking to Casey, who is sort of the main person behind it, and it's just been really cool. I was there between this time, and we had a little bit of interest. We didn't have a lot of people. I think there was maybe some issues with either Gisty or the link that they sent out, so we didn't really have like a lot of people through our specific room. But there were some interesting discussions that have come up in the sidebar and some connections through the University of Copenhagen, and also Twitter and other social media engagement. So it wasn't like, oh, here's 50 people knocking on our door to join the lab from this event per se, but I think it was overall a win because it's always good to reach out and stay in touch with your institutions, but specifically, there's a lot of related interest, and also like just as a kind of professional development note on this front, and I'll go back on camera for this. Like if you're interested in ever having a discussion about how to do stuff at career fairs or engage certain topics, or like do speaking stuff, or how do you get speaking, or how do you get like in that sort of like consultant, speaker, academic, expert role, whatever. And I'm not an expert per se, but I'm interested in doing some of that science communication related stuff. And like that's something we can talk about in professional development sessions, because there's definitely an art to how you do networking about it, how you engage and approach others to say, I want to do this or that. And in my case, like I've known Casey for a long time, and we have a lot of similar interests, and we have a lot of connections. So it was just fine. But that's something, keep that in mind for like if you ever want to have any specific requests for professional development kind of things. That's something we can talk about. But yeah, as far as a general note on like the we have a lot of applications to go through already for things on LinkedIn mostly, and even things to sort out. Like we still have things to sort out with some different people in the lab who mentioned they'd be interested in XYZ task or this administrative task, or someone wants to help out with social media particularly, or writing, like having someone to like take specific notes for the meetings. Like I used to do more of that, but if some specific record keeping would be helpful. So like we're on the verge of sorting out a lot of these needs, and yeah. Oh, one other thing too, I don't think anybody's going to join from it today, but I did mention this meeting to some people from the EA research grant in the UK, and I might say more about that next, but I don't think they're going to stop by, but I did just remind them about the meeting, so we'll see.
All right. Yeah, good. Thanks. Yeah, keep the word going here. So, let me go back. This was Open Chat Forum. We had a lot of things here we were talking about. Ankit mentioned here that he wanted to create a neurocogsi repository. He made a repository.
Did you get invited to the oral group organization, Ankit?
Yeah, I'm in the group.
Okay. Sometime if you ever want to, like, I think you can pretty much find everything in there, but if you have any questions about where things are in that, or like whatever, just I don't know, mention it somewhere on Slack, and we can talk about that, because that's a very good thing to have, and we definitely want to encourage contributions and involvement in GitHub. So.
Yeah, sure.
Yeah. So we have So Ankit, I can't remember where this was in this channel, but he did make some sort of thing.
That was in the ML one. ML, but
yeah, I don't. You mean in the ML channel, or
yeah.
Which data science ML. Yeah, it's up here somewhere. There it is. So yeah, this channel here. This is his library. So this was the thing that FLISCOPT. Yes, this is the thing actually, the demo that he had put together, and this is. Why don't we get to that in a little bit here? Because I was showing the Collab notebook a little bit, but maybe we should go walk through it in a bit. But Jesse posted some resources on multimodal computing and multimodal machine learning in this data science ML channel. So we have a number. Well, there are a lot of things actually posted. So there are a lot of papers. Yeah,
I kind of got excited about that. I did the last week for a variety of things with that I
Yeah.
saw that course, and then I saw all this stuff. What are you going to say?
Yeah, actually, this library was actually like a part of what research I was doing. So initially, it was just like a small project that I was making. Then I started to do some tweakings and just started to play around. So I thought maybe I would make it into some research paper. But then while I was thinking of turning into a paper, I realized that whatever I was making, it's not really usable. So I thought I would convert it into a library so that like anyone could probably use it.
Yeah.
So like that's how it happened.
Oh, good. Yeah, I mean that's great. Yeah, and then so I guess Jesse has this interest in multimodal computing, and I noticed you've been putting a lot of things in the Slack. I wanted to make sure that you're organizing this a little bit better. Like,
Yeah, I put it in a Notion page. It's
Okay,
that's
all
one of the
right.
links on the bottom. You can look at it if you want there. The Notion version of it. It's incomplete, but I'm creating a set of. I'm going to make more specialized pages in the future, but like you can kind of see a layout of some of these things. I don't yet know how I'm going to call it representation learning or just representation in general, but like you can see kind of a collection of stuff from. There's a course from CMU that I'm not necessarily going to say I'm looking into it, but I'm going to be. I'm basically trying to give myself a crash course on some of these things so I could talk about them for the paper I'm going to submit on Monday. And it's going to be like, we'll see how that goes. And I don't expect necessarily to be the greatest paper, but like I kind of give myself that deadline of, okay, for this event I want to submit something. And so this is kind of a collection of resources about it.
Yeah, no, I think that's a very good approach, and I think it's something we've done in the past where we just kind of work around deadlines and say we're going to do it by this date, and you write and you see what you can get done, and then if it gets rejected, that's that's life. But you get this paper that you can refine, and it just gives you like a deadline to like get things done by. Otherwise, you don't necessarily get anything done. You just kind of when I can get to it, I don't know. So yeah, that's definitely a good a strategy. And then I would definitely I like this Notion organization here. So yeah, if you which paper are you referring to there?
Yeah, and I feel like Notion is sort of like just an organization thing, and then it can more formalize into like libraries like Ankit did, or things for GitHub that are more refined by this pages.
Jesse, by the way, I think you're aware of meta resources, right?
Who?
You're aware of that meta resources repository,
right? Maybe.
So what we did was we converted everything in that meta resources repository to an Airtable. So maybe you could do something like that. I'll share the link right now so you can see like what we do actually.
Okay.
Okay. Yeah, thank you. So yeah, that's good. So I want to. I don't want to spend too much more time on the Slack review, but I want to go back and finish up here. Type some loose ends. So we talked about the bioevolution. There's some things as well. This brain is a prediction machine. The music reveals how it works. That's an interesting paper. There's also this thing on neurocausality, and then there's also this thing on might a single neuron solve interesting machine learning problems through successive computations on its dendritic tree. I don't remember if we talked about that last week, but
I don't think so. I think this is something I saw like from Cording's.
Oh yeah, Conrad Cording's paper. So this is a new paper. So there are a bunch of new papers to go over in that channel, and then finally this neuromatch, which we'll revisit that. We have the tracking document here. So I think this is the same one I have up. We'll go through that in a little bit. So, okay, so I think that's all I wanted. And this is the Airtable that Ankit just talked about.
Okay, yeah, thank you.
So that's good. Now, there's Morgan. His camera's on. So I guess now I wanted to move to maybe Ankit will do his demo first on the switch genetic algorithm thing, and then Jesse will give an update on the career materials that he was talking about.
Oh yeah, mine won't be very long, so
Okay.
like it can be moved also. But yeah, you should go Ankit.
So Ankit, can you share your screen?
Yeah, give me a second.
Okay.
I just need to just get things sorted for a second.
Okay. So yeah, that's good. And then later on, we'll talk. I have a little presentation on something that ties into what Ankit's going to present. It's not the same thing, but but it's still something that is maybe tied. Something that involves neuromatch. We'll go over the neuromatch stuff, and then papers, and then that's an hour, I think. So.
If Ankit needs like 3 minutes, I could probably just really quickly do the position paper stuff.
Yeah, why don't you do it while Ankit's getting ready?
Yeah, I don't know how much. Yeah, I'll just do that. It really won't take very long. It's just
Okay.
gonna be.
Yeah.
So, really quickly on position papers. That's what I'm gonna be writing for the thing. I'm just gonna like. It will be just a very review of it, but like it. I'm curious mostly what Bradley has to say about that, because sort of like, in the case of, do I even have? Oh, I don't have it pulled up here. In the case of the submission that we're trying to do for this thing, let me actually just try this. Yeah, it's a very particular like Google Slides thing. Anyway, position papers and arguments, and this kind of reminds me very much of the Conrad Cording content or context content conclusion, and kind of just creating a reason for why you want to do it. This might not be the best version of it that I've seen, but like essentially it's just making an argument for why or why not. There's actually a better, where did it go? There was a much better it's basically creating an argument, and in the case for the upcoming one, we only have 4 pages to kind of create some background and argue why we want to argue our point. But I don't know. Do you have anything you want to say about the position papers, Bradley? While I try to find what I'm looking for.
Oh, so if you could put that, well, I guess you can't, but like the thing on the position papers that you were showing before.
The first one?
Yeah.
This one?
Yeah. So, I mean, this is, of course, organizing your thoughts in terms of introduction, conclusion, and body. And then, like, one of the things, you want to do is you want to figure out, first of all, what you want to argue. So sometimes that's harder than actually writing it, because figuring out the right argument is, both, you have to define what you want to argue. So, sometimes people will do things like straw manning or things like that, which are where they take an idea and they kind of throw an absurdist argument against the wall, and you say, if we do this thing will happen. And of course, it's not likely to happen, but, people use those kind of rhetorical techniques and to make arguments that fit their sort of agenda or their needs. And that's not necessarily what you want to do in a position paper, although people do it. I think a good position paper would be like where you take something in the literature that that's maybe controversial, like representation, say. And you say, I'm going to argue this definition of representations. And this is why I believe this. So, okay, let's take that example, representations. You say, I want to introduce people to this concept. We're going to do some literature review and show that there, a lot of different you want to show like sort of how there's a lot of variation in the literature. You don't necessarily want to show that it's messy, although that's probably true, because then you're kind of like creating this sort of rhetorical opportunity to say, well, there's a lot of literature, and I don't know. I'm probably right because we don't really have a consensus definition. To which someone will respond, well, of course we have a consensus definition, and you're wrong. So you don't want to get into a trap like that. But you just want to review the literature, You don't want to cherry pick references. You want to kind of go through some areas of the literature, and then you say, well, this isn't for, say, what we want to do. So you want to motivate your argument by maybe a specific need in the literature. For what we want to do, it's insufficient. So this is what we think we should have a new definition of representations for maybe like embodied agents, and this is why. And just give some examples, maybe from the literature again, drawing from that and saying, this is a really robust definition because it allows you to think about these things and explore these topics and answer these questions. And then the conclusion, you're just basically reviewing your argument, the main points, and then you're providing like food for thought for later. And then when people read it, they have this argument that says, this is something we should do in the literature. Maybe, someone else was wrong. I've given you those brain and behavioral science papers where, you have the main paper and then you have like 70 pages of rebuttal by different groups, which is like, you have like, they have an open period where like, people can give a response and they say, this part of the paper was good, this part of the paper sucked, and this is why. And then there's like a dialogue there. So, definitely you want to think about that dialogue too. Like, what is it going to look like when I write this? And so, well, why don't you say a little bit about this?
Yeah, I think, let me get this out of here now. I think there's a very particular art, and this is actually kind of a major impetus for some things in terms of frontier map and some cognition feature stuff and understanding trajectories and physical studies. So that way, like Bradley said, you don't want to make a straw man or just create. Like Bradley said, selecting the question or your argument itself is very hard, and also situating your argument in a way that's useful for people coming to it. Because if you make a trash argument against a straw man, or you misrepresent the field itself, like there's no way to save that. Like that's kind of just a waste of time. That's a paper you shouldn't really be writing. And having enough understanding of the field that you're able to situate your argument in a useful way and at least propose, and this is basically what I'm going to attempt to be doing for this thing at NeuronPace anyway, it is, you kind of need to have enough background and articulate, represent some of the diverse viewpoints and say, well, here's what people think that are kind of know what they're talking about, and I kind of see them, but I want to push the conversation this direction. And that's not really an easy thing to do. But it's also like in the context of, I'll try to, where did it go that I want to, did I put it in general? I might have done it like that. Yeah, great. Here we go. In the context of this, here's the actual thing I'm going to be presenting to, like looking for, just a 4-page position paper, which isn't very much. And so it's like, in this context, it'd be talking about metacognition, in these areas, and then how do we situate that discussion? What's the point we want to make? And generally, the point that I'm going to try to make is like Metabrains models, multi-modal machine learning, spatial computing can help in these areas, basically. So it's not quite finished yet, obviously, but I'll leave it at that. And I know we have other things to do, so we can move on. I imagine Ankit's ready by now. So anything else you wanted to say, or just take it on back to Ankit?
Why don't we go over to Ankit?
There we go. I think my screen is done sharing, yeah?
Yeah, I think so.
Oh, great. Which things?
How do I share my screen?
Get onto the bottom of your interface here. It should be this screen with the arrow that comes out.
Yeah, left of the chat and right of the camera.
Just tell me if you can see.
Yeah, you can see it.
Okay, so this is the notebook. So do you want me to go through the repository first, or?
Well, why don't you go through this, and you also had that other document, or you said you had a Medium post that you had. as well?
Uh, yeah, give me a second. That is about Copilot. Yeah.
Okay.
Uh, One second. Somewhere around here. Could someone actually put that in the chat while I'm explaining?
Okay.
For the Medium post?
Yeah.
Yeah.
Okay, yeah. I know where it is. I'll put it.
Should I start then?
Yeah, go ahead.
So basically, I created this library. It's called FLISCOPT, which basically translates to flight scheduling optimization, and it's basically like an optimization library for a flight scheduling problem that I was trying to solve in my research project. So the features that it supports currently are algorithms such as hill climbing, random search, simulated annealing, genetic algorithm, and then you have a variant which is the GA in reverse mode. Then you have genetic algorithm with reversals and an iterated chaining method. So now I'll show you the demo. So first of all, obviously I installed the library. It's available on PyPy, Python package indexer. Now basically the first thing you basically need to do is download this particular text file. The reason being because because the way I've made it is you need to have the text file, and that is the default mode of operation. Now you can define any arbitrary function like this, and you can see the function works, and you can basically optimize this particular function using the algorithms that I provide. So in these steps, what I do is basically if you see over here, you can see that the data folder is outside of all the other folders, so which is exactly what we do. So we are currently in the contents in Colab. This comes under the contents part, and so there if this these lines will create a data directory outside of the contents and we shift it. So we are importing the methods, and this is just an example of a simple genetic algorithm. Uh, and so basically this is the cost curve and improvements over a number of iterations.
Okay.
And I did this for a Grevang function of size 3 for seed 5. So similarly, I'm going to do this for another function. So now this example is for the genetic algorithm with reverse operations. In this, basically first you import it like this. From the GA file, you import the reverse GA reversals and the GA. And then after that, you basically create an object of it, and then you can apply any particular domain and the respective fitness function. So here in this run, I'll be showing for the flight scheduling cost function. It takes a bit of time actually. Yeah, so this is basically the plots you can see and the cost function. And this is one of the method that I basically worked on a lot more. It's called the genetic algorithm with reversal. Guys, can you hear me properly, by the way?
Yes.
Uh, are you sure you can hear me properly?
Yes.
Yeah, it's good.
So in this method, it's like a GA with reversals. So you have a parameter called n underscore k, and another parameter the number of generations. So ideally what we do is when we are creating a genetic algorithm, we say that there'll be a certain number of generations up to which we are only going to evolve it, and so that determines how many iterations basically which are happening. So what n underscore k parameter is doing, so if there are 500 generations and 125 is n underscore k, So let's say we divide it and then we subtract 1 because we don't want it to reverse in the first iteration. So we'll get like 3 reversals, and like each reversal is going to be of 100 back steps. So you can see the objective function is continuously, its cost is being reduced, and this is just the previous run. So in the reversal step, what we do is for 100 steps, you can see that this is like a bit shifted, obviously. For 100 steps or 150 steps, the it will try to maximize it, and then it will again try to minimize, which is back to the normal mode. So what basically this does is by maximizing it, it will try and escape the saddle points, or if it gets stuck in local minimas in the search space. So I'm just going to run and show how it works. Yeah, so you can see basically this is only one. Now if I change 125 to something else, let's say change to 25, so it will again change the number of reversals which are happening. Yeah, so what happened? 1 second, I need to check what happened. uh, mm, mm, yeah, so basically you can change it with respect to that. And what happens is that when you're doing this, it helps to reduce the function. So now you might be thinking, what's the domain? So in this library I have implemented the domains of some benchmark functions. So like each point will have a certain range. Let's say like your function has parameters x, y and z. So the range of the domain of x would probably be between this, and domain of y would probably be between this. And you can basically add more number of variables. So this would be like a b c d f g, so for like n variables. So this is another example that I'm showing, that I'm defining the domain for like one particular variable between minus 1000, and when I multiply by 10, it becomes for 10. So it's like it's trying to minimize a Greenbank function which has like 10 parameters. Yeah, so you can see it's trying to minimize it. And then the last method that I basically worked on was the iterated chaining method. So what the iterated chaining method does is basically, let's say you run a genetic algorithm, you get a solution. Obviously you're getting a solution like this. Now why you just stop? You use the solution, initialize the next algorithm with this solution, and then you get another solution, and then you initialize the algorithm again with this solution, and you keep on going. Now the problem that you get with an iterated method obviously is that if you run for a long amount of time, then the cost will increase like crazy. So I implemented like a small early stopping method, which is like similar to what you find in deep learning. And besides that, what I did was I used the genetic operators like mutation and crossover, which are obviously from genetic algorithms, and I inserted them in between, after, just in between. So suppose you get the solution, I'm mutating it, and then it's going to get passed. So you get the next solution, you're mutating it in between, and then it's going to get passed. So So what usually happens is that when you're doing this iterative method, these algorithms are not really like evolutionary. Like they have their own limits, obviously, and it can easily reach a local minima. So by adding these mutations, it helps you to get out of the local minima again, which is one of the reasons why obviously it basically helps to increase the diversity of the solutions. Just by simple mutations, you can basically increase the overall diversity, which is like one of the principles by which your GA is working. And similarly, what the reversal one does. So this is a small demo of how the iterative chaining works. So in this, I'm importing a random search on a hill climb, and so in this one, what I'm going to show you is for a fitness function for flight scheduling. What if we use random search first and then we pass on the solution to GA? Reversals. This is going to take a lot of time because obviously you have like two sub algorithms running inside it. It's going to take a lot of time, obviously. So the cost which I'm printing is the cost after, I think, each run. So this is the cost after this random search got run. Then you have the cost of the GA reversal. Then again in the next iteration, you have for the random search, then for the GA reversal. And this is going to go for a few steps and terminate. Okay. So in the meantime, I'll tell you like from where I got the idea of iterated chaining. So for those of you who are familiar with machine learning, in machine learning we have a concept which is known as transfer learning. In transfer learning, what we're doing is basically we are using like a pre-trained model and we are using those representations in a new model. And so what that does is basically it's like you the transfer the learned model already has a lot of information, and that will and when you train another model on top of that, it helps you increase your scores and helps you learn a lot more. It's like someone transferred some memory into your head on how you want to crack some exam or something. So you already have a lot of information on how you want to go about it, and just makes your job easier. So yeah, this is should end about now. Some iterations, and yeah, it ends around the 9th iteration. So you can see this is the graph. Like obviously, it's going up, it's going down, it's going up, it's going down. But you can see it ends at the 9th iteration around this, basically 0 to 9 is basically 10. And let's see what's the cost is. The cost of it is again 2356. And if you remember what the cost of our function was, of our single with reversals, it was 2356. So you can see that this method can actually work sometimes, but there are some problems with these methods. Now, what are the problems with these methods? That this method is somewhat randomized. How is it actually randomized? You're using like two algorithms and you're relying on those two algorithms solely, and just you're using mutations in between. So in this manner, when I'm applying a seed, the seed is only limited to the first population initialization, but at other instances you're relying on the stochastic property of these two algorithms, and as a result, Since you're relying on two algorithms, it's already difficult to say like when one algorithm will give a good result on a particular optimization problem, and now you insert two problems and you are basically trying to artificially change the solutions using mutation, and so therefore it becomes really difficult. And especially the main problem that happens is that when you're passing the solution, initializing and re-initializing it again, there's only like a certain amount of new information that you can learn by passing it again and again. So there's always like a saturation point that you reach, which is why like I've used the early stopping. And another problem with this is when you use different ensembles, like let's use the hill climb, for example. When we're using different ensembles, what usually happens is that yeah, you can see again there's a really high amount of variance which is happening. So when you're using different algorithms, you can get really weird and bad results like this. So overall, the method, when it optimizes and gets a cost, if you plot the results, you see that it has really high variance, and you don't want heavily varying results for your problem. You want results which are a lot more precise, and let's say only plus minus 5%, not more than that. But this method will have a really high variance, but the average will not be too bad. And it solely depends on what you're using as the local algorithm. Another reason for using random search first and probably the hill climb is because it again leads to the concept of diversity. So since genetic algorithms, they are working on the principle of diversity, they're using crossover, things like that. My idea was that why not choose like an bad optimization algorithm. Like random search is really bad. It will obviously produce bad results, and as a result, uh, since it's giving me bad results, and after I mutate those results and pass it to a better algorithm, maybe the saturation which is occurring in this algorithm would probably get reduced, and it could possibly result in some better better solutions. But this again, with a pinch of salt, obviously, it can result in really weird outcomes, and it's really experimental. And the final feature that I have is that uh, I, since it's really boring to just run one algorithm, I basically used multi-processing, and you can basically see the results yourself. You can see how bad this cost function really is, like 4,000 something like that. And for our which method was it? For our GAs, it was around 2,356. Yeah, and this is the seeds. So similarly, another example that I'm showing is for the reverse GA, and I'm going to store it, and it will get stored in one of those files, and I'll be printing the result. You can see how fast this GA ran, just 2.5 seconds, whereas in our earlier run it took how many seconds? How many seconds did it take? Probably it took around 9 seconds or something, 9-10 seconds probably. Now you can see the results as well. And this is for an arbitrary function which I defined at the start. So these are the features that currently this package slash project has. And another lastly that I wanted to talk about is that I'm not sure if many of you are aware of this, but the Python is using the C Python interpreter. Basically, Python is written in C, and the interpreter is known as C Python. And there's another interpreter of Python which is known as PyPy. and PyPy is currently in version 7.3, or it uses PyPy is implemented for. Basically, it's like an alternative Python interpreter. But the thing is, when you use PyPy, it's like super fast. Like the results you are getting right now for 2 seconds, for multi-processing probably like the time would get reduced by like 50%. So like these are the things that I've done right now, and I'm thinking of like how I can actually now use these methods that I've implemented for some tasks. Yeah, so that's all.
Well, that was very good. Thank you. Thank you.
So
We could go on about this for an hour, I think, but I didn't want to. I did want to go to other things. So, did we have any immediate comments?
No, it's great. But yeah, I might have more things to say, ask later, but that's good.
Yeah.
so do you want me to talk about this blog?
What is this? This is the post on this.
Yeah, Medium post.
Yeah, maybe go through it for maybe about a minute.
Yeah, sure. So obviously, I think some of you are aware, or maybe not. So basically, there's something known as the GitHub Copilot, and it's basically like an AI which will help you code. So I got access to that like a time back, and this library that I created was created kind of while using it. So in this post, basically I described like how it basically helped me. So you can see like this is just me kind of. You can use Copilot in this manner. If you just take a text file, if you write a statement and write AI, it will just uh, automatically print stuff out. So in this conversation, you can see like how it's saying like Elon Musk created something. Yeah, like I am a human being called Elon Musk. So I ask why is it Elon Musk? So he's like because he's the best at what he does, just weird stuff. Yeah, and like again over here, it's like basically since it's trained on GitHub, it's going to learn what people have already said. So this is like saying that I use Arch, like which is a reference to a meme. Like I use Arch, by the way. So here's just a video I've inserted. So this is an example. That do you want me to talk about the examples or just how it helped me?
Yeah, you can just maybe one example. This one here would be good.
I'll show another example then. Yeah, I'll talk about this. So I just wrote a star search in Python with this comment, and it outputs the entire algorithm. Similarly, if I just write a function for some computer vision task, again you just get this entire thing. Or like create a recurrent neural network using this library. Again, it's so good that will output you the library. And this is another example that while I was writing this, let's say I had the definition of random. So this is of a previous version that I was working on. And if I just write the random search implemented, this is the entire doc string that it can produce from your parameter, which is really great, and it saved me time in the earlier versions, not right now. And again, another problem that I was facing was like while I was testing it, I kind of had problems with the paths and something. This is again a code segment that it generated for helping me run while importing libraries from different paths. Then another thing was when you create the init part of it, like for example, the init will usually have the version number. So when I wrote this line, it suggested me some stuff out of which it suggested me to write the init. The reason being the version number will obviously be somewhere over here. That was again also I found it was really great, which I didn't know about. And the last parts that I found was really great was this file. When I was writing unit tests for testing the library, which is over here, this is like a bash file. If you run it, it will run the test. Let's say which one am I showing? test the algorithms. Yeah, so I just wrote this part, and this is the entire stuff it generated. Not everything, obviously. I've added a few things later on, but it recognized that I am going to write the unit test. It automatically created like a class of it and was able to write the tests on its own to a degree, which was again really great in my opinion. And again, it knew how to basically call the unit test on its own. So a few things which I kind of realized about Copilot is that it's not really dumb, and like let's say like GPT-3, it's trained fine-tuned on GPT-3. So since GPT-3 is trained on a huge language corpus, it understands the language semantics and the structure. So it would really be easy for such a model to be trained on code, and it really understands what kind of design pattern or the abstractions that I'm using. So for example, in my library I was using a certain design pattern which is called the abstract factory design pattern, and many times it would have repetitive code, so it would really understand what kind of code it has to output rather than just output and just recommend something. It takes into context the previous code and also the imports and stuff, so it really works like a language model in essence.
Okay.
And another thing that I liked about it is basically it works not only for markdown files, also for bash files and any kind of stuff. Yeah, I think that's it.
Oh, well, that's great. Thank you. Thank you for the demo and everything. And I, like I said, I wanted to do some other things. So if you wanted to put questions in the Slack for Ankit Grover, please do so. I know there's a lot. If you think about it a little bit, there's a lot that we could talk about here, ruminate about how we could use this, or just more general questions.
Yeah, I would love to use the new method that I've created for any new task, that would kind of show like how good it actually is or how bad it actually is in practice.
Well, we'll talk about how bad it is, like how bad or good it is, and how that might be. We might want to think about that outside of algorithms. So I'm going to talk about that in a little bit. Now I wanted to go on to some things here on our neural match submissions. So the submissions document, well, this is a submissions document more generally. Jesse was talking about this metacognition submission at NeuroIPS. This is for, I don't remember what the topic is. We can fill this in later. It doesn't really matter. But this is due October 4th, so this is on Monday. And Jesse's working on this. And hopefully, Jesse, are you on track for this? Or
For the NeuroIPS one?
yeah, metacognition.
Yeah, I mean, it's going to be... I'll be working on it probably into Monday, but I am doing that. So.
What is the topic?
Basically, it's sort of an exploration of multimodal ML and spatial computing as how can they relate to metacognition and some like allusions to our Metabrains models efforts and how to kind of create. I'm going to try to write a way to create an infrastructure for metacognition stuff.
Okay. Yeah, that's good. Definitely. Please, maybe next week we can talk a little bit about the paper that you have, where you are with it. I mean, you'll have submitted it by then, but we can talk about like look it over and just kind of think about like some of the. It's a 4-page thing, but just kind of like that'll probably foster a lot of thinking about like this area. I find that if you do a paper like this or a presentation, it really does frame a lot of the issues. So definitely let's revisit that. We also have this NeuroMatch submissions document, which is, I think, here. So this is, I'm adding to this. Okay, so we have some new stuff on here. So we have a bunch of things that are possibilities. We can follow up on some of the talks that we've given before. We have these different ideas here, and like some of these like Gibsonian information, we have a talk already for that. We can go out, and we have a preprint which needs to be put out too. So we have those. Some of these things, again, this is a poster that can be turned into. Some of these things are a little less defined. So this is something Jesse's fleshing out now. Economic Metabrains is a paper that Daniela has written, and then maybe we'll be involved in it as well. Inhomogeneity correction, this is something, and neural decoding. I think Krishna put these on, maybe. Those are, Oh, was that?
Okay. Can you hear me?
Yeah.
Okay. So I put these two topics, and I am not sure about neural decoding because I'll be able to work on that also in the time. But if time permits, so I'm planning to present these two topics along with Bradley and Jesse. So if anyone among you is interested, feel free to add your name here and contact us on Slack. Regarding this, if you are new to NeuroMatch, I'll suggest you to try it because it's a really good experience to get to meet a lot of new people, different set of domains among neuroscience, and you can learn a lot from them, and that's a really nice experience. So, feel free to add your name here and contact us regarding this. That's it. And regarding neural decoding, it's a very interesting topic, but I think it will take more time than the other one to meet the slides and extract. So maybe I don't think that I can do it, but if I get a chance, so I'll try my best to work on it also. Especially if you are interested in neural decoding, you can do a little work on that along with you. So collaboration is always there. Thank you.
Yeah. So if you're interested in collaborating, you can put your name here. If you're not, then you can cross it out or whatever. And just so we have an idea of who wants to do what. But then critically, we need to actually write an abstract, and that's like maybe 300 words. I would check with the NeuroMatch website before you write it. I think it's 300 words. But we want to have an abstract here. We want to have a link so people can review it. Then we want to make sure it's submitted, so we can say yes, it's submitted, or no. And if it's not, then we can revisit it maybe for something else. I see Jesse's adding things in here. And then, by the time we have, so hopefully when we get things submitted, we can have, then we can start working on the presentation.
Yeah. And if you are new to it and don't know what to write and how to write, how to structure it, so you can see our previous year's abstracts and get an idea how it's done, and previous year's slides, so just for reference.
Yeah,
actually maybe next week. I know we have no time left this week. Well, we have a lot of things to do, but maybe next week we could just do like a little tour of past NeuroMatch stuff, because some of these things are direct follow-up to that. I just added two. I just added two. New to that document things, and development in critical periods is something that I've worked with Anusha before on, and she may do that. I'm not that. Those are both sort of question mark type things, but. And also Avery, who's done a lot of work with Cognition Features and allostatic stuff. Maybe those are sort of more there to see if placeholders. And if you're interested in those things, ask me about them in Slack, and you can also put your name there. Just mentioning those things are on the docket as well. But almost certainly, whatever I do for the MetaBrain or the whatever my first one is, there metacognition stuff, there's going to be a version of that sent. Like that's going to happen on my end. The two I just added less so, but if enough people show interest, that could be make it more likely to happen.
Yeah. Yeah. So again, this is, deadline is coming up sooner than we think. Oh, thank you, Morgan. Morgan said really interesting. And then this is the document. I put it in the chat here. So I think that the permissions are open. So if you want to look through and, if you find something interesting, sign up or ask questions about. We have a NeuroMatch channel in the Slack. So
Yes.
Right here. So NeuroMatch channel. We'll just use that. So that's good. So now I wanted to move on to this thing, and I've been teasing this all meeting. And this is this idea of switching. So Ankit talked about algorithmic switching, switching between, reversing the GA and things like that. But it turns out that there's a lot of stuff in nature, and this is not algorithmic. This is going to be all natural examples, more or less, on switching and how switching can enable adaptation and can enable different constraints and things like that. So I put this in quotes because I don't know if this isn't really a unified theory. It's just like a bunch of evidence from different domains of biology and cognition. So the first thing we can observe is that the switch is a zeroth order cybernetic system. And what I mean by that is it's a switch like you see on the left. You turn it on, you turn it off. There isn't really any nuance in between on and off. It's just like up or down. And you can characterize this with a Heaviside step function. So in neural networks, they often use this to produce a binary output. You might have something happening here and there's a threshold, and the threshold is instantaneous. It just turns on or turns off. And there's no regulation here. There might be some regulation that leads to that switch, but this is like a very sharp transition. There's no there's no gradient there. So that's the way you characterize it. There's also something called a first order phase transition, which isn't exactly a switch, but it switches from one material to another. So this is the switch from liquid to solid nitrogen. It's a state change or phase change that occurs at a critical point. And so there are a lot of things that lead up to this. So, you might say that to turn a switch on or turn a switch off, there are a lot of decisions in my brain that lead up to that. But this is essentially a zeroth order cybernetic system at its core. But you also have these other things going on. So these other things going on are, other sort of things like in the biology of a system that lead to an behavioral output. And so in bacteria, there are a couple of different phenomena that are switch-like. So one is that in bacteria, some bacteria with flagellum, they tune their nanomotors to differences in the environment. So there's a highly variable environment, and bacteria can actually switch their nanomotors, which drive this flagellum, in different ways. They can switch it from clockwise to counterclockwise, and this switch is controlled by a set of genes that respond to the environment. So when they're, the water is turbid, or when it has like some sort of turbulence, they can switch their motor, adaptively to help them swim. So that's one switch. It's just back and forth from one direction to another. But there's also this other switch that occurs during when a bacteria is exposed to different carbon sources, and so this is a difference in the growth rate from poor to rich carbon. And so, generally speaking, we would expect maybe like a gradual increase in the growth rate, or some sort of gradient of growth rates relative to carbon concentration. But in this case, you actually see shifts, distinct switches or shifts in the regime. So, you have a poor carbon source, the growth rate is low. A rich carbon source, the growth rate is higher, but that function has a step to it, and it has a switch. So it implies an internal switch somewhere in the bacteria. So we talk about internal models in cognition. You also have internal models in things like bacteria, where you have gene networks that are turned on or turned off. Speaking of which, we have these experiments that were done. This is a systems biology approach to looking at this cis-regulatory input into this gene. So this is a LAC-Z system, and it's called a LAC-Z repressor. It's something you find in an E. coli that has, it's an operon where you have a regulatory system where you have something that turns the gene on and off at the front, which is the promoter, and then you have the gene itself, which is expressed or unexpressed by the switch at the front. And so this is this LAC-Z system, and in this set of experiments, they actually were looking at the plasticity of this input function. So the input function is generally something from the environment that triggers this switch. It either turns the gene on, turns the gene off, or it regulates its output. And so they did this, they built like an artificial LAC-Z system, and they actually looked at using like a genetic representation what kinds of problems it could solve in terms of logic gates. So they're able to, they have this elaborate input function on this LAC operon. They're able to, mutate it and do other things to it. And they find that you get these Boolean AND gates and OR gate logic. So you can basically replicate Boolean functions using this type of LAC-Z system just by setting up the switching mechanism, setting it up in different environments and mutating it. So another question they asked when they found that you can use this sort of logic to represent this, you can use the system to represent this type of logic, is that if you want to, if you introduce point mutations, do you ruin the regulation sort of gradually, or is it something that's more robust and then relies on some switching mechanism to keep it robust or to make it, to make sure that it's functional? And so they introduced a bunch of point mutations into this artificial system, and they found that it doesn't ruin the regulation completely. It actually results in different ways to integrate the inputs. So you see in this system, it's where you get, you introduce point mutations to this type of LAC-Z system, this switch, where the LAC-Z regulator regulates the gene and then it produces an output. It's not, it's a switch at the, in terms of like whether it's on or off, but mutations don't necessarily cause switching. It's more subtle than that. And so this is an example of the logic gates and some of the things that they tested this on. This is a paper by Kashtan and Alan, and I think that's the varying environments can speed up evolution. So they were actually able to put these artificial systems in a bunch of different environments, and they were able to vary the environment. And so the takeaway from this paper was that they varied the environment like more and more. So the more environmental variation there was, it speeded up evolution because the individual sort of LAC-Z systems that were maybe more suited for this varying environment were able to survive and produce these kind of outputs. So that was maybe a little bit confusing, but I can put this in a more biological context. This is a theory of human brain growth. And the idea here is that, there's a question of whether, we, in our hominid ancestors and in our primate ancestors, that there's been enormous brain growth in humans compared to our ancestors, hominid ancestors and primate ancestors. And the question is like, what drove that? So people think, well, it's tool use, food. This is a theory that says that there was a lot of climate fluctuation, maybe about, in the last several million, in what they call the Pleistocene, which is maybe 3 million years ago to about maybe 10,000 years ago. And this is where you had a lot of glaciations and a lot of dry periods, and there was a lot of switching back and forth. So, you think, well, as humans were evolving, you would have this need to survive these different environments. You couldn't move all over the place. So, what enabled sort of this adaptation? And it turns out that what enabled the adaptation wasn't evolving a bigger brain than evolving a smaller brain. It was evolving this ability to have a big brain that would allow us robustness to these shifts. So you would have a bunch of different climates within a couple generations, and it was far too frequent for evolution to respond. So the most fit phenotype was to have a large brain that allowed for culture, that allowed us to adapt to these different things in a very general way. And so these are some of the graphs that show this connection between global climate change and brain growth.
Yeah, that's really interesting. I don't want to derail this, but I definitely would like to look more into that. I was totally unintentionally looking at this earlier this week myself, actually, and how brain size developed and our organs, our stomach changed in terms of using like meat consumption and fire for meat consumption, and how the availability of different animals or plant matter during these different times affected this. So it's like the other side of the coin of what we're saying here. So it's cool that it comes up in this way, that the brain and the culture that came along with it further other anatomical changes in the body too, or like coincided synergistically with them.
Yeah.
With it.
So yeah, that's human evolution. Then the rest of this is going to be about sort of human cognition and maybe animal cognition, also machine learning and robotics. So this phenomenon of attentional switching, and I've taken like some elements out of the literature here to kind of build this argument that attentional switching is something that is also this sort of switch controlled by an internal system. And so the attentional switching is where you assume that attention is the spotlight, where you're focusing in on different things in the environment. And so if you assume that, you're assuming the sort of centralized control of a single spotlight, and it's moving around the environment, paying attention to different things. And so you can do these experiments where you have two tasks running, and if you have two tasks running simultaneously, you sort of split your attention between the two. But if you distribute them in space, you pay attention to one task, then another task, and this switching has to occur where you move from task to task. And so this switching requires a sort of cost of capacity or time. So if the tasks are too closely associated in time, you can get a significant cost of switching, your attention breaks down and you lose focus. But it also depends on sort of the control mechanism. So maybe attention isn't controlled in a centralized manner. Maybe it's, maybe in some cases you can pay attention to multiple things at once. But also that, you have this sort of, if the tasks are very similar, you can switch between them without a problem. But you still have that switch that's occurring in the brain. And so if attention, say, for example, in a robot, if you had attention where you distributed it across multiple processes that were autonomous, you could pay attention to 50 things in the environment. But then you'd have to integrate them. And you have this same problem where you need to sort of prioritize different places in the environment that you're paying attention to. And so there's this problem of switching yet again, where you're switching between things in different contexts. So, I did this because, there's a cognitive psychology literature, but there's also a machine learning literature on attention. And we deal with attention, particularly in multimodal systems where you have different forms of information, different modalities, and you're paying attention to different things. So, but then there's this thing that I did in the lab once where I looked at the switching between environments. And so the idea of these experiments were to look at the physics of the environment, the forces, the light, and the surface, and how those supervise the nervous system to enable plasticity and learning. So the idea here was that we had a system where you would learn under one regime. This is a common paradigm in motor learning research, where you would learn a task in a certain environment. Then you would have some interference, so you would modify the physical environment in some way. So you would unlearn what you just learned. And then you would reintroduce the original environment, where you would relearn things. And the idea is that you're switching between two environments. And then in the third set of trials, you would maybe recover what you learned here, and then this unlearning trial would either interfere with that or augment it in some way. That's the idea. And so this is the interface. We used like a touch force feedback system where you would reach out and grab things. You could introduce different types of materials, so you could learn on one type of material. You would unlearn on another type of material, so you might learn on a magnetic environment. You would unlearn with a honey environment, which is like a sticky sort of, hard to manipulate environment. And then you would have one where there's no force feedback at all, or it's like on an icy surface. And so you can do all these different things. And this is EMG trace, actually, from these experiments. And so that's one way to do this. Another way is to have a virtual environment where you're doing something like playing golf. And in this case, people were playing golf in an environment where they were just kind of like mimicking this motion, and it was being played back to them on a virtual environment. They had a controller where they would play this game. They would putt, and they would use an actual putter, and they would, try to drive the ball in. But then you also had this case where they were doing it with a weighted club, so the club had some weight, some material in this chamber, and it would weight their interactions, and so it would kind of interfere with that. And so this is stimulus switching, where you're able to modify how you're getting environmental information, and then it's affecting your learning. And so that's the last type of switch I wanted to talk about. But that's the idea behind switching. And I did this because I wanted to introduce a lot of these concepts of switching and of how you can see this across different types of biological system and how it interacts with the internal model.
No, thank you. I would like to see a lot of things in the presentation for obvious reasons. There's a lot of that concede a lot of the stuff about the metacognition stuff and how having a space that affords the switching and understanding the context, and there's a lot of, in a good way, it gave me a lot more ideas to think about for the paper that I'm trying to stuff and articulate in there. So anything there are a lot of papers. I don't know if there were papers that did you were referencing some of the papers that you worked on in the past there that you wrote.
That last part was something I had done in the past. Yeah.
Yeah, I'll look at all that, and if you could send the presentation itself, I'll take a deeper dive into it. I know we're at the end of time here, but yeah.
Morgan said in the chat, I would be interested to know more about the inhomogeneity correction problem, and that was one of the things in the NeuroMatch submission. So I think that's Krishna who proposed that. So we can get in touch with Krishna on that. And then Ankit said, oh wow, our ideas are actually related. I might need this for my paper. So yeah, I'll share those slides and we can talk more about that. Okay, thank you, Morgan, for attending. And I wanted to spend 5 more minutes for people if they don't have to go. I just wanted to go through a couple more things, but those are just kind of finishing up here. So let me share my screen again. All right, so yeah, I'm not going to get too much into anything. I wanted to. So our Metabrains paper, I always do this for every paper we make. We have the citation ages, so we go through the citations and we look at when they were published. I hope this graph is here. Here it is. So the idea is that, in a lot of machine learning papers, everything is within the last 5 years, which is maybe not good for the field because you don't get a historical view. This is our Metabrains paper. It's not on the archive. These are the distribution of dates that we have for citations. So we have one from 1884. It was actually the Flatland reference that I put in. And then we have some other references from the past. So I think this is a nice distribution of citation ages. It says that, we're kind of looking at sort of historical references and maybe digging into that a bit, but also we have a lot of more recent papers, as you might expect. So that's the citation ages of that paper. I also wanted to talk about maybe another paper. Actually, I had Ankit. Ankit, not Ankit Grover, but Ankit Gupta, who I worked with the group about 2 years ago. He got in touch with me, and we submitted this developmental Bratenberg vehicles paper for review. But he said he had worked on his part of that more over last summer, and he actually got a GSOC. He was a GSOC student this year. He's been trying for a couple years, and he hasn't been able to get in, but he's been able to work on his simulations, and I just wanted to show a couple screenshots of that. So he had some recordings here. He has this software, I think, available on GitHub. I'll show you the videos and I'll explain them.
So this is what he was working on this summer?
Yeah, this is what he had been working on, but this is something he worked out more this summer.
Okay, I'll have to follow up with him. That's cool.
So this is these are all Bratenberg vehicles, which if you can look that up to know what that is. And then these stimuli are different types of stimuli that Bratenberg mentions in the book. They're different. They're supposed to evoke different emotions. And in the vehicles, you can simulate these emotions by their movement, by the way they approach the stimulus. So he has these stimuli of different types This is a love-provoking stimulus. This is a cowardness-provoking stimulus. And you can see that, like, the agents in this population of agents will behave according to where the nearest stimulus is. So this 2A is moving, and you can see the agents are moving away from the stimulus. They steer away from it. In the love stimulus, they start to aggregate around it. And this has to do with the way that these Bradenburg vehicles are wired. His Bradenburg vehicles are all static, but given the sort of stimulus, it's just dependent on how they're wired. There's a wiring for each type of the one that responding optimally to a certain stimulus. It's too much to get into now, but basically, this was one of his simulations. He had one where he fixed this the stimuli in space. So this is where the agents are moving, but the resources are fixed. And so you can see that they're doing the same thing. They're kind of avoiding some and gravitating towards others. It's like in 3A, the love-provoking stimulus, everything's quiescent. Whereas in, 2A and 2B, they're like moving around it, or they're, aggression and cowardness. And then aggression, they're really moving around, and they're, maybe bumping into one another. And just with the cowardness, they're just avoiding it. So, he's mapping these things to different types of rudimentary behaviors. And so this software, I think, is available on GitHub. He sent me the applications, standalone applications here. So if you're interested, I can share it with you. This is going to be incorporated into the newer version of this paper. And so that's good. He's made progress on that. I'm glad to see that. So the final thing I wanted to talk about was this, let's see, there we are. I wanted to talk about this paper. I thought this was kind of cool. I found this. This is about virtual reality and putting zebrafish in a virtual reality environment. And this is, the title of this is Zebrafish Capable of Generating Future State Prediction Error. Show improved active avoidance and behavior in virtual reality. This is something that, of course, is related to what Ankit did, but this is actually using real zebrafish and a closed-loop virtual reality system to train adult zebrafish. So they use this system. It's not like the type of VR that we use with big glasses. It's more like a visual stimulus that's generated they'll put the zebrafish in a tube, and at the end of the tube there will be these visual cues, and they can manipulate the visual cues to manipulate the behavior. So it's a little bit different, but that's something it's actually quite a powerful model for animal models, because you can do a lot of things with these virtual, you can simulate different sensory channels and modify them in ways that the animal wouldn't necessarily experience. So analysis of the neural activity of the dorsal pallium during training revealed neural ensembles assigning rules to the colors of the surrounding walls. So they had walls around the chamber, they would change color, and they could actually measure how the rules are assigned to these changing colors. Additionally, 1/3 of fish generated another ensemble, which becomes activated only when the real perceives scenery, so they're generating scenery on these walls and the fish are perceiving them, shows discrepancy from the predicted favorable scenery. The fish with the latter ensemble escape more efficiently than the fish with the former ensembles, and by escape, they can create an escape task where they have to escape from a chamber. They put them in these little water-filled chambers and they do things. So they're able to integrate the behavioral experiments with the neural recordings with this virtual environment. Our results suggest that zebrafish can be used both principles of goal-directed behavior, but with different behavioral consequences depending on the repertoire of the adopted principles. So this is, this is a closed-loop system. It's where you're generating something in the environment. There's feedback. The fish observes it, and then there's feedback in terms of the behavior. And they can actually, connect this with the neural recordings and modify how things are presented. So it can be an actual closed loop, and they can do some really interesting things with this model. So this is the experimental setup. You have the fish. It's got a lens here where it's measuring brain activity. It's this optogenetic activity. You have electrodes here where it's delivering feedback to the fish based on its behavior. You have this display here. and it's in this case it's not in a free floating environment. It's just kind of fixed in this environment. So and then they're measuring a certain part of the brain. They're able to detect neural activity in some of these cells, and these are some of the results. So they have these they have this go no go task, which is something that you see in cognitive psychology, but this is something you can also do in animals like zebrafish. You could deliver a shock if it's no go or go, and this allows for the sort of reinforcement learning type paradigm where you're reinforcing certain behaviors over others. And so this is the example of the experiment. And then they had their findings, which we talked about. And like blue is dangerous, red is safe. And you have this, the fish behaving accordingly. And so, they just have variations on this go, no go task where they have an original rule and then they have a reversed rule. So this is another example of switching between things where you have the shock was associated with the blue color, shock was associated with the red color. This is a way to make sure that your manipulation is working, because if it's just a matter of maybe they don't like blue for some reason and you're associating the shock with that, well then you don't know if there's feedback there. The learning might be because of the blue color, so you want to rule that out. So but that switching is interesting because what does that mean for the behavior? You can design the experiment another way and look at if you keep reversing the the paired stimulus, the environment and the shock, what is that result in? So we don't know the answer to that from this paper, but
Hi, sorry to interrupt, but so when they have the original and the reversed trials, was it randomized? Initially, the original is where this shock in the blue associated with blue, and reverse is where shock is associated with red. So was this random, or was it sort of was it predetermined within the trials?
I think it was. Well, I think it was. It may have been randomized. I'm not really sure. Okay. So they do this right here. They have an adaptation here. Then they have the original rule for 80 trials, and then they have the reversed rule for 60 trials. So it's they go from the original rule, and then they go to the reversed rule. And then you can also randomize it too. I mean, you can set this experiment up a number of ways, right? And depending on the question you're asking. So but in this case, they did do an original rule and a reversed rule. But then they didn't look at the outcome of that. They just wanted to see whether it would do the same thing for the reversed rule.
Right. Got it.
Yeah.
Thanks.
So I think that's all I wanted to say about this paper. I don't think they have any really nice figures of the in virtual environment. Just kind of the summary, figure 9, where they're doing this. You have these rules assigned to colors. So you're saying avoid the blue, go to the red. You're having this prediction where you have, you can look at backwards moving scenery versus real scenery. If the scenery is real, you stop. If it's backwards moving scenery, you can associate backwards movement. There's prediction error, which can then be the zebrafish in its brain will correct and minimize, and then over time this is learned, and then you end up with this behavior. So behavioral adaptation. So that's all I wanted to say about that paper. I think that was a nice overview, and I'll put that in the Slack as well. Morgan said, I love this idea. So thank you for attending, Morgan and Krishna and Madhuri and Ankit and Jesse. I think this is a good meeting. Do we have anything before we go? Did you have any comments or questions?
I would just reiterate, please send me that switching material.
Yeah.
And no, we've got a lot of stuff going on, and I just reiterate this for new people and in general. Just because people aren't in this meeting doesn't mean they're not in the lab. It doesn't mean things aren't going on. It's really cool that former, I forgot his last name, Ankit.
Gupta.
Yeah, Ankit from GSOC is doing that stuff. Daniela's got a paper going, and a lot of things that are sort of, we didn't hear from Angela, wasn't here this week, but a lot of things are going on with Angela. So just a reminder, there's a lot of things going on, and definitely ask questions in Slack, and if you want to collaborate on a project or an idea, or you see a submission upcoming for a neuromatch or anything else. A lot of things going on. So just putting that out, and that was a great meeting, and thanks to everyone sharing what they had today.
Yeah, thanks for attending, and we'll talk in Slack.
Thank you.
Thank you.
Do you mind if I could share my draft related to what I'd written? So that I was initially, when I started, even I was looking for like a different biological perspective a little bit, which is where I got this idea of, which is somewhat switching only, if you can see in the graph of my reversal process. So I was thinking of maybe adding a little more of that perspective into the paper rather than keeping it totally computational. So maybe if you wanted to discuss, like I could share my draft with you.
Yeah, that'd be great, and I'll share the slides, and we'll come together. I think that mix of like algorithmic and biological is important. I think when you want to show universal principles, that's one way to do it, is to show it in algorithms and then show it in biology.
Yeah, so where should I share it? In the personal message or?
You could share it. You can share it in a personal message. That would be good.
Yeah, I should do that.